Hi everyone, my name is Thin Nguyen and I am a PhD candidate at the University of Illinois Urbana-Champaign. In this video, I will summarize the main result of this project, the AGORA Galaxy Simulation Comparison Project, Paper 9, Part 2, studying the effect of a major galaxy mergers on the stellar morphology of a Milky Way-mass Galaxy Progenitor. This is the second part of the two-part series of this project focusing on the effect of the major galaxy mergers. A little bit about the Agora collaboration. So the Agora collaboration is the multi-institutional and international collaboration who focus on comparing galaxy simulation codes in order to understand the code better and to enhance the predictive power of simulations in studying galaxy evolutions. One of the big product of the Agora collaboration is the Cosmorun Zoom-in Cosmological Simulation Suite, which include 9 state-of-the-art simulation codes. These codes are calibrated to have the same initial conditions, mass resolution, star formation prescription, gas cooling, heating, UV background, and analysis tool. The two main differences among the 9 codes are the code architecture and the stellar feedback implementation. This project is the paper 9 of the Agora series, and this is the part 2 of paper 9, which focused on the stellar morphology effect of the merger. The part 1 focused on star formation effect is also uploaded on arXiv at the same time with this paper. So here we show the major merger that we study. The left plot here shows the gas projections during the mergers going from the beginning of the mergers to the end. And we see the secondary galaxy falling in from the bottom left of the plot here and merge with the main galaxy. The formatting of the code name reflects the stellar feedback implementation that each code uses. Code with blue names are codes that use kinetic feedback in their model. Codes with black names mean that they don't use kinetic feedback. Codes with the asterisk means that they use radiation pressure or delayed cooling in the code. And codes with the dagger sign means that they use the super bubble scheme in their implementation. To make the analysis easier, we also divide the merger sequence into 4 stages: the info stage, the first passage stage, the coalescence stage, and the post-merger or post-coalescence stage. The main result of the paper is that we find that this type of stellar feedback of each code impact the stellar morphology of the merger remnant. So we find that for codes with kinetic feedback, the galaxy become more compact and develop a disk after the mergers. And this compaction and disk formation happened earlier in the interaction during the info or the first passage stage. So here we have the stellar radial mass distribution for codes with kinetic feedback. And we see that compared to the old stellar populations, the distribution become more compact around the first passage stage, which is the yellow distribution here. In terms of disk formation, we see that the disk to total ratio increase after the merger to above zero point 0.5, and the info and first passage stage account for around 20% of the disk mass for these code. In contrast, code with only thermal feedback, which are Enzo and a T, undergo compaction and disk formation later in the merging interaction. Specifically, compaction and disk formation happen primarily during the coalescence and post-coalescence stage, which is reflected here, that we see that the distribution doesn't become more compact or doesn't become more compact until the coalescence, which is the red portion here. And most stars also form during the coalescence stage. So 74% and 90%. In terms of the disk formation, we see that the disks comprise mostly from stars formed during the coalescent and post-coalescent stage. These stars account for more than 80% in the disk. Last but not least, codes that don't use kinetic feedback but use the delay cooling and superbubble scheme do not undergo either compactions or disk formation. Rather, the merger remnant expand compared to the pre-merger state, and we see here the disk to total parameter do not increase much and they stay below zero point 0.5, which means that the galaxy, the merger remnant, is still dispersion dominated. Another main result that we find is that the rotational angular momentum axis of the merger remnant disk align with the orbital angular momentum axis of the merging interaction rather than the pre-merger rotational angular momentum axis. So this plot here, we see that the angle between the rotational angular momentum axis of the merger remnant only differ by at most 30% compared to the orbital angular momentum axis of the merging interaction, but can differ up to 140 degree compared to the pre-merger rotational angular momentum axis. This means that the secondary galaxy, it carries the infalling gas, and these infalling gas retain the orbital angular momentum to form a disk later in the merger remnant. Last but not least, we also compare our simulation result with the Santa Cruz semi-analytic model, and we find that the stellar mass and the stellar half-mass radius agree with the semi-analytic model with some tuning. However, the central dark matter fraction and velocity dispersion do not agree well between our simulations and the semi-analytic model. Thank you very much for your attention, and you can refer to the paper for more details of the project. Thank you.